For our next example, we are going to apply the orthogonal decomposition theorem to answer a question about two vectors w and z and their corresponding distance. So the prompt goes as follows. A vector u in Rn and an orthonormal basis S for subspace W of Rn are given. Use S to obtain the unique vectors w in W and z in W perp. So it's two different vectors in two different places such that u is equal to w plus z. So this means you want to take a given vector and rewrite it as the sum of two vectors, one that's in w and one that's in w's orthogonal complement. Once we do that, we want to use our answer to find the distance from u to w. So the first thing we're going to do is find vector w, and to do that, we are going to use the orthogonal composition theorem. To find vector w, we find the dot product of u and v1 with v1, and add to it the dot product of u with v2, and then v2 as well. And v1 and v2, by the way, are these two vectors in S. So first, if I do the dot product of u with v1, that is 1 over radical 5 times, and then I can multiply the components, 1 and 1, 2 and 2, negative 3 and 0. That just makes 5 as my dot product there. And then v1, I'm just recopying it. So lots of stuff going on here, but luckily it simplifies easily. And then for u with v2, again, I'll do the same thing. I'll multiply u with v2. I'll keep the coefficient outside. I'll multiply the components, 1 with negative 2, 2 with 1, negative 3 with 3. That's going to give me out just 9. And then I multiply that by v2 itself. Then when I put this all together, 1 over radical 5 times 1 over radical 5 is just 1/5. That I'm multiplying by 5. So that just cancels out to just a 1. So I have 1, 2, 0 from the first. And then from the second, 1 over radical 14 times 1 over radical 14 is 1/14, but I have a 9. So that is 9/14. And then negative 2, 1, and 3. At this point, you're welcome to use a calculator or start using common denominators, whatever you prefer. But if you put these two together, the final result should be 1/14, 32, 19, and negative 27. So that's our vector w, and this lives inside of the subspace w of Rn. You can also leave everything over 14 inside if you want, but you don't have to. All right, next let's find vector z. So if you recall, vector z is the, when we're looking to find this here, we draw it parallel from the vertex, and z is the difference between u and w. So to find z, that's the easier one. We simply subtract u minus w. So for that, we do 1, 2, negative 3 minus 1/14, 32, 19, negative 27. So again, you can use a calculator, you can use common denominators, whichever method you prefer. And when you do that, you should get 1/14, negative 18, 9, and negative 15. Last, to find distance. Again, distance is the norm, so that means we want to take the square root of every component of my vector z. So I'm going to square negative 18/14. I'm going to square 9/14. And I'm going to square negative 15/14. Add them all up, take the square root, and it simplifies nicely down to 3/14 radical 70. If you're interested in another example, example 3 in your textbook works out one that's very similar. if you'd like to see another one in good detail. The last part of this section is on the orthogonal projection matrix. While we don't cover linear transforms directly in this course, some of the verbiage does slide in to this part, but I think it's important because as we move into the next section with least squares and coming up with the line of best fit and the parabola of best fit, you're going to see this notation and concept. So the orthogonal projection matrix, we denote it as P with a subscript of W. The columns of an orthogonal projection matrix are basically the images of standard vectors under an orthogonal projection operator. So we're just moving around those standard vectors, 1, 0, 0, etc., which we can do using the method we just described in the problem that we just did. To keep it pretty simple, the formula for an orthogonal projection matrix is listed here. It's C times C transpose C inverse, all times C transpose. I'll leave the details to you if you'd like to read a little bit more about it. For our purposes, we will primarily be using it from a computational standpoint to help us find some things out. And this relies a lot on linear independence, invertibility, etc. So that's nice ties back to chapter 2. So the use that we're going to start talking about now, and then in the next section, is this idea of a closest vector. We want to minimize distance from one vector to another, and that'll help us with least squares. So here, I give you a subspace and a vector. We want to find the orthogonal projection matrix, and then the vector in W that is closest to V. So to get started finding what we need, we can start by saying a vector is in W if and only if it is orthogonal to both vectors, just like our example from before, in the given set. So just like our early example, we're going to take each vector and write it out as a system to be solved. x1, x2, x3, x4, x1, no x2, plus x3, no x4. We can write it out like that. And if we go ahead and make a matrix out of it, solve the system, augment on 0, 0. Let's see. So if I go ahead and 1, 1, negative 1, 0, 0, 0. So there augments on the last column. No x2, 1 x3, no x4. Okay. So if I go ahead and augment that on, the RREF of this matrix is going. Okay, so if I find the RREF, I can then, like we did earlier, write this out as a system. X1 plus x3 equals 0. X2 plus x3 equals 0. So if I write it out using the general form, looks like my free variable here is x3. And then x4 is free also to be whatever it would like. So I can write out the general form as x1 equals negative 1 x3, x2 equals negative 1 x3, x3 is itself. No word on x4, so I can put that there. And then let me just move myself so I can finish the rest. Okay, so then for x4, I have nothing at all, so that'll just be a bunch of zeros and a 1. So we can say that a basis for W is for the orthogonal complement can consist of these two vectors here. And you could check if you're interested. These vectors are indeed orthogonal to the given ones. So now the question says, find the orthogonal projection matrix. The orthogonal projection matrix is equal to the matrix C, and that is the matrix formed by the columns of the columns that are here. So I can just make it a 4x2 matrix. So I take matrix C, multiply it by C transpose C inverse. That's an uppercase T. Spoke too soon. So that's an uppercase T here. Inverse goes on the outside, and then C transpose again. So this is the formula for an orthogonal projection matrix. At this point, some of these computations are ugly, so I would recommend using an online calculator for this, using this as your matrix C. And when all said and done, it comes out beautifully. Maybe it would have been fun to multiply out, but I don't want to add to your homework time. So you get out these nice numbers here. Random 3 on the bottom right. So that's our orthogonal projection matrix. And the cool news is when we want to find the vector that is closest, all we need to do is multiply our orthogonal projection matrix by vector V. So we simply take this matrix here, 1, 1, negative 1, 0, 1, 1, negative 1, 0, negative 1, negative 1, 1, 0, 0, 0, 0, 3. And we multiply it by V, which was given on the outset. And it turns out our closest vector is 0, 0, 0, 2. So after all that, lots of zeros in the final answer. So there you have it. I spared you the agony of doing the multiplication out by hand, but this is the orthogonal projection matrix. Again, I'm going to keep it computational because as we move into the next section, the focus will be finding lines and parabolas that best fit, and this will be one of many steps that needs to be done. And I don't want to get you guys bogged down in the mechanics of it. So hope you enjoyed this video, and I will catch you in class soon.